Alrighty, hey, we're back, and I switched to a different computer, which actually has the Smart Notebook program on it. So you can see that I fixed that. That fixes the little mu naught I thing. So Amperes law is closed integral b dot ds equals mu naught I enclosed. How do we figure out I enclosed? You just swirl your hand around in a direction around wires, and if your thumb matches the direction of the current, you take it as positive. If your thumb's opposite the direction of the current, then it's negative. And that's what this says here, and this is the example here. So if we look at this, integral b dot ds would be moving around this way. Our thumb points up, this wire's up, so that's positive I. And as we continue to come around, here we are, our thumb's still pointing up. This would be negative I here. So that would be the total current would just be the sum of those two. So looking at this, here's like a little sample problem. And so it asks you, it says the figure shows three equal currents of 4 Amperian loops. Rank the loops according to the magnitude along each greatest first. So I envision taking my right hand with my fingers moving in the pointed in the path that I'm moving the cursor. My palm would face the computer screen at this point, and then I'd wrap around behind and like that. And so my right thumb would point up, so this would be positive. My right thumb would point up, so this would be positive. And when I get here, my thumb would still be pointing up, but this current's going down. So that's a negative one. So negative one, positive one, cancel out, positive one. This is a plus one. If we do that same trick here, and we circle around here, my thumb would point up, current's going down, that's negative. The path sneaks behind this wire. That's what they're trying to show you. So that'd be zero contribution from this current. And then around here, if you imagine swooping your hand around this with your thumb pointed up, that would be a positive one. So negative one, positive one, zero. When we come over and look at path C, if we pass our hand around this way, then your thumb would point up, the current points down. This would be negative one. And curling around here, this would be a total of positive 2 because they both point up and your thumb points up. So for magnetic field outside a current carrying wire, this hopefully is going to look really familiar to you, just like Gauss's law, but for Amperian loops. So this entire thing is the wire. They've made it look really big, and there's the current. The current is coming out at us, and they want to know the magnetic field at some distance, little r away from the wire. So the blue part here, this is all the wire, this is the tube, and then out here is where we're trying to find the magnetic field. So mu naught I enclosed is closed integral b dot ds. Mu naught I enclosed is just equal to bs. That's the integral. Yeah, I know. I heard it too. And then mu naught I enclosed is equal to b, and then s is 2 pi r. S, it's a good point, good time to mention. S just means path length. So S is going to be whatever distance you're traveling, and every single one of these paths is going to be a circle. So S pretty much always is going to be 2 pi r because that's the path of a circle, that's circumference. And if we stop and look at this, we get B equals mu naught I enclosed over 2 pi r, which is exactly the equation that we got when we did all of this, right? So the Biot-Savart law, you can get the same equation, or you can just use Amperes law and rock to it right away. And so if we look at this, the part I have circled in green, all this is a constant. Mu naught's a constant, I enclosed is a constant, 2 pi is a constant. So whatever's going on after we're outside the radius of the wire, this equation decays as 1 over r, which is all I'm trying to show you right there. And that's probably a good spot to pause for this one.